Breathe out. Go ahead, just one breath. Nothing dramatic. You do it about 20,000 times a day without thinking about it. But that breath you just let go, that little puff of warm air, where does it go? Most people would say it disappears. And I want to tell you something. That is one of the most spectacularly wrong things a person can believe. That breath does not disappear. It goes on a journey. And that journey is, I think, the most beautiful story in all of physics. So let's follow it. You just exhaled what came out. Mostly nitrogen, a good bit of oxygen, some water vapor, and about 4% carbon dioxide. That 4% is interesting because you made it. Your body pulled oxygen out of the air, burned some sugar in your cells, and stitched carbon onto it. Those carbon dioxide molecules are yours. You manufactured them. They carry atoms that just seconds ago were part of you, part of your blood, your muscles, the lining of your lungs. Now here's the first thing people don't realize. How many molecules are in that single breath? The answer is staggering. About 25 billion molecules. Let me say that differently. 25 followed by 18 zeros. That's in one ordinary breath. Not a deep breath, not a dramatic gasp, just a regular forgettable exhale. That number is so large it's almost meaningless. So let me make it mean something. Take all the grains of sand on Earth, every beach, every desert, every riverbed. The total is roughly 7.5 billion grains. Your single breath contained more molecules than all of that. 3 times more. One breath, more particles than every grain of sand on the planet. All right, so you've got this little cloud of 25 billion molecules floating away from your face. What happens next? At first, not much. The cloud drifts. If you're inside, it bumps against walls, mixes with the room air. If you're outside, the wind catches it. But something is already happening at the molecular level that you cannot see, and it is ferociously fast. Each molecule in that cloud is moving at roughly 1,000 miles per hour. 1,000. They are not drifting lazily like cigarette smoke. They are screaming through space, smashing into neighbors, ricocheting in random directions. A single nitrogen molecule at room temperature collides with another molecule about 5 billion times every second. 5 billion collisions per second, each one sending it off on a new heading, a new angle, a new trajectory. The path any one molecule traces looks like the scribbles of a drunk ant. Physicists call this a random walk. And a random walk has a peculiar property. Each individual step is totally unpredictable. You cannot say where a molecule will be after the next collision, but the statistical spread of trillions of molecules doing this simultaneously is completely predictable. It follows a diffusion equation, and what that equation tells you is beautifully simple. The cloud of molecules spreads. Always, inevitably, you cannot stop it, you cannot reverse it. You could build the finest walls, seal every crack, and still those molecules would eventually work their way through because at the atomic level, no seal is perfect. The random walk always wins. Within 10 seconds, the cloud from your mouth has expanded to about 1 meter across. Within a minute, it has filled a small room. Within a few hours, molecules from your breath are leaking out windows and doors, mixing with the outdoor air. Winds pick them up. Convection currents in the atmosphere, driven by the sun heating the ground unevenly, carry them upward. Jet streams grab handfuls and fling them thousands of miles. Weather systems churn and tumble and stir the atmosphere like a cook folding batter. Within a week, molecules from that one breath are scattered across a continent. Within a month or two, they've spread across the hemisphere you're standing in. They've crossed the equator. They're mixing into the southern skies if you started in the north, or vice versa. And within about a year, this is the part that startles people. Within roughly 1 year, the molecules from that single breath of yours are distributed more or less uniformly across the entire atmosphere of the Earth. Every cubic meter of air on the planet, from the summit of Everest to the alleyways of Tokyo to the middle of the Pacific Ocean to a shepherd's campfire in Mongolia, contains a few molecules that were inside your lungs. Let that settle for a second. 1 year, 1 breath, the whole Earth. The atmosphere is enormous, a thin shell of gas weighing about 5,000 trillion metric tons, and yet it mixes so thoroughly, so relentlessly, that your tiny contribution of 25 billion molecules manages to spread itself across the entire thing in about 12 months. Now, I want to push on this a little harder because there is a famous calculation that physicists love. It goes like this. Julius Caesar died on the Ides of March 44 BC, stabbed 23 times on the floor of the Roman Senate. As he fell, he exhaled one last breath. A gasp, probably. Maybe a groan. It doesn't matter. What matters is that 25 billion molecules left his lungs for the last time. It's been over 2,000 years since then. Those molecules have had plenty of time to mix. Plenty. They've been through every storm, every monsoon, every trade wind pattern the Earth has produced in 20 centuries. They are as uniformly mixed as anything can be. So here is the question, right now, in this breath you're currently taking, are any of the molecules from Caesar's dying gasp in your lungs? And the answer is yes. Not probably. Not maybe. With near certainty, about one of them, roughly one molecule in every breath you take, was part of Caesar's last exhale. The math is straightforward, and it's worth walking through because it shows you how big numbers play tricks on your intuition. The total number of air molecules in Earth's atmosphere is about 10 to the power of 44. A gigantic number. Caesar's last breath contained about 10 to the power of 22 molecules. So the fraction of the atmosphere that belongs to his last breath is 10 to the 22 divided by 10 to the 44, which gives 10 to the minus 22, an incredibly tiny fraction. One molecule out of every 10 to the 22. But wait, you're not sampling one molecule. Every time you inhale, you're pulling in 10 to the 22 molecules of your own. And each of those has a 1 in 10 to the 22 chance of being a Caesar molecule. Multiply 10 to the 22 samples by a probability of 10 to the minus 22 per sample, and you get roughly about one molecule per breath. That is not a metaphor. That is not poetry dressed up as science. That is arithmetic. You are at this very moment breathing in a piece of Caesar's last moment on Earth. And if you think about it for another second, you realize the implications are much wider than one Roman dictator. Not just Caesar, Cleopatra, Galileo, Newton, your great-great-grandmother, the first human being who ever spoke a word, every person who ever lived and ever breathed, their exhalations are mixed into the air you are using right now. Every breath you take is a census of history. The atmosphere is a library of every breath ever taken, and you're reading from all of it simultaneously. There is something unsettling about this if you let it sink in. The air is not clean. I don't mean polluted, I mean it is populated. It is thick with the molecular residue of every living thing that has ever exchanged gas with it. You share your air with everyone. There is no private atmosphere. There never was. But I promised you a journey, and we've only covered the first part. Mixing. Spreading. That's just physics doing what physics does. Randomness making things even. The really beautiful part comes next. Those carbon dioxide molecules from your breath. The ones you personally assembled. They don't just float around forever. Something grabs them. A leaf. Somewhere on Earth, maybe in a forest in Brazil, maybe in a rice paddy in China, maybe in a patch of grass in your own backyard, a green leaf absorbs one of your carbon dioxide molecules. And I want you to appreciate what is about to happen because it is one of the most remarkable chemical tricks in the universe. The leaf is running a chemical factory powered by sunlight. Inside its cells are tiny structures called chloroplasts. And inside those are stacks of membranes studded with a molecule called chlorophyll. When a photon of sunlight, a single particle of light that left the surface of the sun 8 minutes ago and traveled 93 million miles through empty space, when that photon hits a chlorophyll molecule, it kicks an electron to a higher energy state. That energized electron triggers a cascade of reactions, a chain of molecular machinery, so precise it makes any human factory look clumsy. The end result is this. The leaf takes your carbon dioxide molecule, which is one carbon atom bonded to 2 oxygen atoms, and it rips it apart. It strips away the oxygen atoms and releases them back into the air. Free oxygen, the very stuff you need to breathe. The carbon atom, the one that was part of your body just a year ago, gets woven into a sugar molecule, glucose, 6 carbon atoms in a ring, surrounded by hydrogen and oxygen. Your carbon atom is now part of the structure of a living plant. Think about what just happened. Sunlight traveled from a nuclear furnace 93 million miles away, hit a leaf, powered a molecular machine, and grabbed a carbon atom out of thin air and built it into food. That is not metaphorical. That is the literal physical process. A photon from the sun reached down and rearranged the atoms from your breath. And what does the plant do with that sugar? Everything. It uses the sugar to build cellulose for its trunk and branches. It uses it to make proteins for new leaves. It stores it in seeds and fruit and tubers. It pumps it down to its roots. Your carbon atom might end up in the skin of an apple, in the petal of a flower, in the wood of a tree that stands for 300 years, in a grain of wheat that becomes bread on someone's table, or maybe an insect eats the leaf. Now your carbon atom is part of a caterpillar. The caterpillar becomes a butterfly. A bird eats the butterfly. Your carbon atom is now in the breast muscle of a sparrow, powering flight. The sparrow dies, falls to the forest floor, and bacteria consume it. Your atom returns to the soil, gets absorbed by a root, enters another plant, gets eaten by a cow, becomes part of a glass of milk, and ends up in the bones of a child. This is not poetic exaggeration. This is what atoms do. They cycle. They get passed from body to body, structure to structure, organism to organism. There is no such thing as new matter on Earth. Every atom in your body has been part of something else. Many things, countless things. The carbon in your fingernails might have been in a dinosaur's tooth, in a fern from the Carboniferous period, in a volcanic eruption 300 million years ago. And I want to be clear about what I mean. I don't mean something vaguely like it. I mean the exact same atom. Not a copy. Not a similar one. The very same carbon atom. Atoms are not consumed. They are borrowed. Now let's follow a different piece of your breath. Buster, not all of it goes to plants. A fair portion of your exhaled carbon dioxide lands in the ocean. The ocean is a vast carbon sink. Carbon dioxide dissolves in seawater, reacts with water molecules, and forms carbonic acid, bicarbonate, and carbonate ions. These dissolved forms of carbon drift through ocean currents. Some of them get taken up by phytoplankton, the tiny floating plants of the sea, and enter the marine food web. A fish eats the plankton. A bigger fish eats that fish. A whale eats several tons of those fish. Your carbon atom, the one from your quiet little exhale, might end up in the body of a blue whale cruising through the Southern Ocean. Or something more patient happens. The carbonate ions combine with calcium in the water, forming calcium carbonate. This is the material that corals are made of. It's what shellfish use to build their shells. Tiny organisms called foraminifera make their skeletons out of it. When they die, those skeletons drift down slowly through miles of dark water, settling on the ocean floor. Over millions of years, this rain of tiny shells compresses into limestone. Your carbon atom becomes rock. The white cliffs of Dover are made of this limestone. Compressed shells of ancient sea creatures, built from carbon that was once in someone's breath, in someone's blood, in the atmosphere of a younger Earth. The cliffs are a graveyard, but also a monument, a record written in calcium carbonate of carbon's long residence in the sea. But even rock is not the end. The Earth is not still. Fine tectonic plates shift. The limestone gets subducted, dragged down into the mantle by the slow grinding of continental plates. Down there, under unimaginable heat and pressure, the calcium carbonate breaks apart. The carbon combines with oxygen again, and the resulting carbon dioxide rises through cracks and fissures, sometimes erupting from volcanoes. Your carbon atom, after spending 100 million years locked in stone at the bottom of the sea, comes screaming out of a volcano and re-enters the atmosphere. And the whole cycle starts again. Do you see what is happening? This is not just a circle. It is circles within circles, nested loops of matter, cycling through every compartment the Earth has to offer. Short loops where carbon bounces between air and leaf and animal and air again over a few years. Medium loops where it sinks into the ocean, drifts through deep currents and comes back to the surface in centuries or millennia. Long loops where it enters the rock, gets buried under continents and returns through volcanism over tens or hundreds of millions of years. Each loop operates at a different speed on a different clock, but they are all running simultaneously, all moving atoms back and forth across the boundary between living and non-living, between air and water and stone and flesh. And every one of these loops is driven by energy. The short biological loops are powered by the sun. Photosynthesis captures sunlight, fixes carbon, and the whole food web runs on that captured solar energy until it eventually degrades into heat. The long geological loops are driven partly by the sun, partly by the heat left over from the Earth's formation, and partly by radioactive decay in the planet's interior. Every cycle has an engine, and every engine runs on physics. Now I want to go further. I want to zoom out from carbon and think about what happens to the rest of your breath. Those nitrogen molecules, the ones that made up most of what you exhaled, they have their own story. Nitrogen is more stable. it doesn't react as easily. Most of it just bounces around the atmosphere for a very long time. But some of it gets pulled into the soil by nitrogen-fixing bacteria that live on the roots of certain plants. The bacteria convert atmospheric nitrogen into ammonia, which plants use to build amino acids, the building blocks of proteins. So your exhaled nitrogen might end up in the protein of a soybean, in the muscle of a person who ate that soybean, in the DNA of their children. The water vapor from your breath condenses. It might join a cloud, travel 1,000 miles, and fall as rain on a mountainside. That rain seeps into the ground, feeds a spring, becomes a river, and flows to the sea. Or it gets taken up by the roots of a redwood tree and pulled 300 feet into the air through the magic of capillary action and transpiration. Your water molecule, exhaled on a Tuesday afternoon, might be hanging in the canopy of a forest by Thursday. Every single piece of that breath, every molecule, every atom continues. Nothing stops, nothing rests, nothing is wasted. This is what the first law of thermodynamics really means when you strip away the formalism. Energy is conserved, matter is conserved, nothing is created or destroyed. It is only rearranged, and the rearranging never ever ends. But I want to tell you the part that gives me the deepest chill, because we have been talking about cycles on Earth, about atoms moving through air and ocean and rock and life. That is beautiful enough. But the atoms themselves, where did they come from? The carbon in your breath was not always carbon. There was a time very early in the history of the universe when carbon did not exist anywhere. The Big Bang produced hydrogen, helium, and a tiny bit of lithium. That's it. No carbon, no oxygen, no nitrogen, no iron. Nothing you are made of existed in the newborn universe. So where did carbon come from? It was manufactured, cooked, forged inside a star. Not our sun, an older star, a much more massive star that lived and died before our solar system was born. Here is what happened. A massive star, maybe 10 or 20 times the mass of the sun, spent millions of years fusing hydrogen into helium in its core, just like our sun does. But when the hydrogen ran out, it didn't simply fade away. It had enough gravitational pressure to squeeze the helium atoms together, and at temperatures of about 100 million degrees, helium nuclei began fusing into carbon, 3 helium nuclei crashing together to make 1 carbon nucleus. This is called the triple alpha process, and it requires such specific conditions that the physicist Fred Hoyle once argued there must be a particular energy resonance in carbon that makes this reaction possible. He predicted it from pure logic, and when experimentalists looked, they found it. The universe is tuned, in a sense, to produce carbon. But the star did not stop there. Once it had a core full of carbon, the squeeze continued. Carbon fused into oxygen, oxygen into neon, neon into magnesium, silicon into iron, layer after layer, like an onion, each shell burning a heavier fuel than the one above it. The whole process accelerated. Hydrogen burning lasted millions of years. Helium burning lasted hundreds of thousands. Carbon burning lasted perhaps 1,000 years. Silicon burning, the last stage, lasted about a day. One day, then the iron core could burn no further because iron sits at the bottom of the nuclear binding energy curve. Fusing iron does not release energy, it absorbs it. And with that, the star's core collapsed. In less than a second, a region the size of the Earth was crushed into a ball about 10 miles across. The outer layers no longer supported came crashing inward, hit that incompressible core, and bounced. The rebound sent a shock wave outward at a significant fraction of the speed of light, a supernova. For a few weeks, that single exploding star outshone its entire galaxy. Hundreds of billions of stars, and one death scream was brighter than all of them combined. The explosion scattered the star's guts across space. Carbon, oxygen, nitrogen, silicon, iron, gold, uranium, everything heavier than lithium, flung into the interstellar medium. Those atoms drifted for millions of years, mixing with gas and dust from other dead stars, forming a vast, slowly rotating cloud. And then gravity started pulling that cloud together. It collapsed, it heated up, a disk formed. At the center, a new star ignited. Our sun, around it, leftover debris clumped into planets. The Earth coalesced from that debris about 4.5 billion years ago. The carbon in your breath, the oxygen in your lungs, the iron in your blood, every bit of it was delivered to this planet by a star that died before the sun was born. When you exhale, you are not throwing something away. You are returning borrowed material, material that was lent to you by the atmosphere, which got it from the biosphere, which got it from the ocean, which got it from the rocks, which got it from the dust cloud that formed this solar system, which got it from an exploding star. And after you, it keeps going. Your last breath is not an ending. It is a handoff. Those molecules will enter leaves and fish and raindrops in the lungs of people not yet born. They will be part of laughter and shouting and whispered secrets and the crying of infants. They will be part of the 21st century and the 30th century and whatever comes after that. They will outlast every building, every monument, every civilization. And eventually, billions of years from now, when the sun swells into a red giant and the earth is consumed, those atoms will be scattered back into space, free to drift through the galaxy, maybe to be swept up into a new cloud of gas, a new collapsing nebula, a new star, a new planet, maybe new life. The atoms do not care about you. They have no loyalty, no memory, no preference. A carbon atom does not know whether it is in a diamond or in a dump. An oxygen atom does not know whether it is in the breath of a queen or in the rust on a fence. But the atoms are faithful in their own way. They follow the laws. Conservation of energy, conservation of matter, conservation of charge. The laws of thermodynamics, the rules of chemistry and nuclear physics. They follow these laws with absolute obedience, without exception, without fatigue, without negotiation. And those laws ensure that nothing you are made of will ever be lost. Rearranged, yes. Scattered, yes. Transformed beyond recognition, certainly. Lost, never. So that little breath you let go at the beginning? It is not gone, it is just getting started. And I think the most astonishing thing, the thing that I keep turning over in my mind, is that this entire magnificent journey from your lungs to a leaf to a fish to a cliff to a volcano to a star, all of it is described by a handful of rules that fit on a single page. Conservation laws, thermodynamics, gravity, electromagnetism, nuclear forces. That's the toolkit. And from that toolkit, nature builds everything. Every cycle, every transformation, every exchange of matter and energy across 13 billion years of cosmic history, all of it follows from a few elegant constraints. If that does not take your breath away, well, at least now you know where it goes. Tell me this. That breath you just took, knowing what you now know, does it feel different? Does the air feel like it belongs to you, or does it feel like you belong to it?